So hello everybody, welcome back to the afternoon session of the second day, and now we will have the panel. So the scope of the panel will talk about power module packaging, the different vision from a device manufacturer, let's say, up to system integrators. So the panel, we have seven intervenants during the panel. They will make a short presentation, each of them, and we will invite them on the stage. And then we will go through some questions to introduce the different topics, and we let open discussion. Then, if you have questions, do not hesitate to continue the discussion between the participants. So, I invite the first presenter. So it's Victor Veliadis from Power America. Thank you.
Okay. Thank you very much. And it invited me to be here presenting experiences you never say no yet. You always have to follow this guy. Well, I think I'm loud enough, right? So anyway, okay. So very briefly, I wanted to say that in the case of silicon carbide and GaN of wide-bandgap, when it comes to modules, it's the perfect storm. You got the high current, you got very high voltage, you got frequency, a lot of current. So today, it's not an exaggeration to say that the module is really a bottleneck. Okay, if you want to fully exploit the benefits of silicon carbide and GaN devices, you need to improve the modules. You can see here there are a lot of rooms for improvement, from the substrate to whether you want to obviously eliminate the wire bond so you don't have parasitic inductance. Thermal management is very important. Die attach, there are different techniques and different ways to do it, and it's a co-design type of effort. You need people from the mechanical, from the electrical, physics, materials people. That's the only way you can get it done right. So with respect to Power America, we get together with our members, and the members decide on projects that are useful to the whole membership. And modules has been an area where all the members said, we want to run pre-competitive projects, we want to solve problems. So this is four of the first four projects we did in modules, looking at everything from 3.3, 6.5, 10 kV, right? The high voltage silicon carbide, looking at the high frequency for, for GaN. And then we had a module competition here. We put about 850,000 of member money. That was cost share by 330,000 from the performance, 1.2 million in projects to demonstrate silicon carbide, to demonstrate high frequency. And the outcome of all these projects that were carried out by universities belongs to all the members. So that's the idea. So the members decided to pull their money together and look into modules. So there's a lot of work to be done. And if we want to, again, get to the full potential of silicon carbide and GaN technology, we got to take care of the modules so it's no longer a barrier. Thank you.
From ISiC.
Hello, everybody. My name is Dieter Elisabeth. I'm from ISiC Technologies, a GaN on silicon fabless company based in Israel. We are concentrating our efforts and activities around automotive drivetrain inverter, mainly. So we are really demonstrating that you can replace silicon carbide or silicon IGBT in the 400-volt battery cars with GaN on silicon. That's our aim, and this is where we are putting all our efforts. I will have later also a speech about it. This is just an overview of what we have done so far. You see on the right side a complete inverter which was running on a dyno test at a European OEM, WLTP testing with more than 350 amps. And we are basically doing everything back to back. So from chip development, power module integration, up to inverter testing, so that we are basically able to demonstrate the potential of GaN on silicon. So like Victor also said, the chip itself is nothing without the package, and this is where the reason for this panel discussion as well. Thank you very much.
Thank you. So the third panelist, it's Daniel Hoffman from Wolfspeed. Thank you.
Thank you. Yeah, welcome back, everyone. Yeah, it's working. Yeah, so Wolfspeed is actually doing plenty of stuff. We have the bare die in our portfolios. We have plenty of discrete devices and power modules. This is divided in basically 3 business units. Yeah, so we have the bare die business unit, we have the discretes and the power modules. And for the bare die business unit, it is really important to work with customers on the packaging, implement the dies into constructions to get the best out of it. And yeah, the tinier the devices get, the higher the current density, the better the package must be. So we are reaching some limits where you cannot use bond wires anymore, where you really need to move to copper clips or new technologies. And some old style packages like discretes, which is then for more the consumer market. On the power module side, we do have our own kind of specific and nice ways to do it and make it reliable. If, to take a look at this slide, besides the die top attach, there are many ways to put a die into a package. We always have to think of thermals, of reliability, and also manufacturability. So design to manufacture is always a big contributor. On the discretes, many are using still discretes for certain powers, but when it comes to higher powers, you definitely need to go to power modules to get the full potential of silicon carbide, which you also can see here on the right-hand side. It's a thermal path from the device through the die attach down to the cooling path, which is super important. And the lower we run on temperature, the more power you get out of it. So cooling is also the key. Thank you.
Thank you. So the next panelist, it's Michael Gößler. Yes, thank you.
So, hello everyone. My name is Michael. I'm leading the R&D development team for the business unit of AT&S. AT&S is actually a PCB manufacturer, also packaging. And what we also do is embedding, and embedding for GaN as well as from SiC devices. And what you can see here is actually a typical stack up what we are currently using for an automotive inverter. So we have actually the standard cell in the center where you can integrate the MOSFET in a resin compound. You have a high side and the low side. And then you attach with sintering 2 copper blocks on the top and on the bottom side. And below attached, you see either a possibility to go with a thermal prepreg or with a ceramic material. I will talk later in the session more about this stuff. So it's just to give you a teaser what we can do. And actually, I see a lot of possibilities what we can do now in the future with this kind of technology. So we see especially 3-level and more level inverters as a very interesting technology, especially with embedding. There we see a big possibility for the future. We see SiC as the first step, but we also think maybe GaN in the mixture or somewhere else, could be a possibility for the future. Main challenges for embedding, is build up the trust. It's a new technology, and automotive never likes new technology. So we have to establish this trust to the market. So that's the main challenge. Nevertheless, we also see a huge opportunity because PCB manufacturing has huge capacity out there. So you don't need to establish all the NRE costs what you typically have for module manufacturing. You have already a lot of existing capacity on the market, which will help up to boost the EV market. From the material side, we can use up to 200 degrees Celsius. That's not an issue for us. We use materials with a very low CTE, which are in line with the SiC and GaN materials. We have isolation ready for very thin dies, so between the top and the bottom side of the die, to have the isolation there. We can have also the DPC as a standard solution on the bottom side for the isolation to get the heat out of the system. And we see also further opportunities for sensing in the module integrated already. That's all in a nutshell. Thank you.
Thank you. So next panelist, it's Thomas Gottwald from Schweizer. Thank you.
Thank you, Elena. So this was a good startup for the embedding technologies, and I will also present the advantages of embedding technologies to you. So what we developed together with our partner Infineon is a so-called embedding device. So it's a component which is used for being embedded into the PCB. So it's not a bare die embedding technology, but we're using a lead frame with a cavity, and inside the cavity we are mounting the semiconductor. This is crucial to dissipate the heat which is generated in the application. And with spreading the heat inside of this standard cell, you can achieve very low thermal resistances. But this is only one effect where we started from. What we also learned is that you can gain higher efficiency by embedding because we have very, very little stray inductances. So we made samples where we found stray inductors less than 1 nanohenry. And this means you can switch very, very fast. And fast switching is one of the preconditions to also go for efficient switching. So what we also showed is that with the embedding technology, you can save 65% of the switching losses that you typically have today in a module, in a direct comparison. And therefore, the automotive industry is keen on this kind of technology because they just get more out of their battery, more range, and even more reliability. Because what we are doing is we do the interconnection between the PCB and the component and the lead frame with an electroplating process, which has a very high reliability. So it is approximately 10 times to even 100 times more robust than a typical power module with bond wires, for example.
Thank you. Sorry.
There was one chart for the efficiency, but I will point it out later in my talk in the afternoon. Just a short glimpse. What you can see is a direct comparison of a module with a silicon carbide device with a switching loss and an embedded device with a switching loss. And if you take them into consideration, you can see you can still save 65% of the switching losses by going for embedding. Thank you.
Thank you. Okay. So the sixth panelist is Hidaka Shiori-san from Mitsubishi.
Yes, thank you very much. My name is Shiori Hidaka from Mitsubishi Electric Europe. Now coming back to the conventional power module. Okay.
Say something. Bit close to your.
Okay. It's okay? So then coming back to the conventional power module, what is the packaging? So packaging from the functional point of view, we have 4 functions. One is the interface with the system and the chips. And also the modularization, so make some switching between combination with the power semiconductors and also the sensors. Also the thermal management, so how to reduce the thermal path to make this packaging. And also protection. So this is the main topics for the packaging. Also the technical point of view, you can divide it in 4 technical domains. One is the die bonding, second one is interconnection. The third one is the insulation substrate. And also the encapsulations. We can combine such the technologies with each other. Then this is a very famous figure. Our colleague, Professor Koller from ETH Zurich presented. So power electronics 4.0 and power electronics 5.0. I will try to translate to power module. We started the hockey puck from 1950 or 1960. Then we have the IGBT module and the MOSFET. Then we started the conventional power module. Then third generation, we have the wide-bandgap devices. But this is the first generation. Just implemented the materials, high-cost materials, to increase the junction temperature or some kind of switching speed. Then we are now talking about the generation 4. So we are using wide-bandgap devices. Then package should be designed from specialized design. For example, lower inductance or lower conductance. and also a bit in function as well. Then maybe in future, we have to discuss about the eco design, zero emissions. So we have to discuss about the life cycle assessment, recyclement, and recyclement and reusability. We'd like to discuss about the packaging 4.0 and 5.0. Thank you very much.
Thank you. Yes, so the latest panelist, it's Mr. Koros Muaber from Volvo.
Maybe you should put the next one. I forgot to put the title.
Just go on.
I can say we have as a Volvo. Here, okay. As a Volvo, we have some concern about the different technology that will be introduced, and okay, we know most of the benefits of these technologies. For example, for the embedded technology. We have two right here that they can explain that one more than me, but we have our concern as well. And we think about this chip vendor. We have a chip supplier. They have this technology is a little, like I say, it depends on the chip. Which chip we could fit to the embedded technology. And we, from the automotive perspective, we don't like to work only with one chip supplier. We don't like to have a one source for the chip, that we need to have these competitions. Another concern that we have here is the reliability and the lifetime for the embedded technology, although they will come. they try to convince us, but still we like to make that one and to see how it works. We are going to have a project to work on it, to make a prototype, and to see how it works. But we can see, you will see that we can see a lot of opportunity for that one. Also, intelligent power module. I think this is I think you know the GAN system or Infineon. Before it was a GAN system, we have got this power module. We have tested that one a little to see how it works. Okay, it couldn't fulfill all requirements, but still is very good for the initial design, I can say, as intelligent. But intelligence also, level of the intelligence is very important for us. Which one is the PowerPoint? This one? Oh, yes. We can have only, for example, power module gate driver, or it could be power module gate driver plus power supplies. It could be even all the caps, like this one, that you can see power supply, driver, caps, and everything we have, and then this is a good. But our concern as a automotive is the complexity, diagnostics of that one, if some component, and also if one component fails here, what will happen? And also scalability and the modularity is our concern in this technology. And also GAN power module, also, okay, we know that the GAN is coming, and then we have worked a lot, and we hope that, we will see that we have even made some inverter for that one. And our concern is more cost right now. GAN should not be such expensive. Theoretically, it should be even cheaper than the silicon. But it's not possible right now. It's in even the prices that we have received up till 2035. I think it's not so big gap between silicon carbide and the GAN. I can say it should be much cheaper. And also we don't have any high voltage GAN for all. For example, for most of the system that they are going to the 800 volt, 900 volt GAN is not enough. And then we need to go to the, for example, multi-level technology. And then it means cost. That is also another. And also thermal conductivity again by itself, device is low. That's also a concern. Maybe it's good from some perspective. And also short circuit scenario for the GAN. We couldn't find, we have tested 3 4 different solutions with the help of some people here. And one of them only was a solution right now, but that one is actually put so much stress on the component. Still, we cannot use the DSAT that we are using in silicon carbide. The device will be broken before we can reach to the DSAT that we need. And reliability of the GaN as well, but it goes, I think, can be solved. And the last one I can say is the multi-level power module. Okay, we like to have a multi-level inverter. And we have made a 500 kilowatt multi-level inverter with a GaN. And up till now, we have tested up till 350 amp. And again, with one of these GaN supplier, and here. And then our concern right now is this cost that we have discussed. Also, we can see the complexity of the power module and driver that we are going to have for that one. And you can see the footprint is very big. Look at that one, how much big it is. I cannot put that one in an inverter. As our colleague mentioned in Scania, that you're going to make that one integrated in the housing, in the EDU. Even the next generation is going to go even closer to the electric machine in the winding, close to the winding of the electric machine. These cannot go over there. This footprint is very big, actually. And this is the reason that totally we think that we have a lot of concern for these new technologies. Power module, if we can make, they can solve the many problems. We can benefit from the low parasitics. We can benefit from the better thermal conductivity. We can benefit from the, I can say, different aspects. But which power module? Should we go to the, for example, embedded technology as the one solutions that we are thinking about? But if we're going to use the GaN in the future, in inverter, we don't have any solution to go to the multi-level, because at least we don't have any high voltage GaN in the mass production for the 800 volt system. If you go to the multi-level, if you're going to have a lower footprint, we don't have any solution to make that one smaller. And if you're going to make that one smaller, either we need to make very complex power module, or we can that one inside maybe some technology like embedded technology to use that one. These are our concern as one of the OEMs in the market with all these new technologies that is coming. But I'm sure that with this people, we can solve all the problem. I'm sure. Thank you very much.
Thank you.
Thank you.
Yeah. Okay. Okay, so now let's start with the main discussion. So we will select some subject that we would like to treat. And actually the first subject, if you can make a top 1 challenge that you have in your either your design or integration, which is, and how you solve it or how you think it's solved. So you think what is the really most important things that you have to select when you design your power module or you manufacture or you integrate? Who wants to start?
The challenge, you mean that the challenge in the package?
Difficulties, yes. We are talking about packaging. Good question.
Okay. Okay, so for us, of course, we can utilize a lot of the technology, so mainly focused on the materials. Especially that we have more than 20 years experience utilize epoxy resin as encapsulation materials. So this is one unique point from Mitsubishi Electric. But also the power wide-bandgap devices. So now we are strongly focused on the layout of the chips and how to reduce the inductance. This is our challenge, and today's main topics related to the packaging.
To improve. Okay, thank you.
Okay, one of our major challenges might be the availability of components. So for the embedding process, you need adapted components. So the technology of the semiconductor is the same, but the surface finishing is different. So we need to have a copper surface plating on the top side of the component to be compatible with the laser drilling process and the electroplating of the micro-vias. So not every component is available and not every size is available. So this was a huge hurdle in the beginning. That's also the reason why it took pretty long to bring embedded to the market. But for low voltage embedding, we are already in serious production. For high voltage embedding with silicon carbide devices, this problem doesn't seem to be so big, because if you talk to the big 5 silicon carbide manufacturers, everybody has copper at least on his roadmap. Some of them are further down the road. Some of them are still evaluating whether going for copper or not, but this will not be a hurdle anymore. So in the future, we will see that embedding will play a crucial role also in the power electronics market.
Good. So from our side, it's mainly a lot of complexity in the different configurations what we have to solve, yeah. And the configuration of different multi-level versus two-level, yeah, is quite complex in the simulation point. Yeah, how to bring things together, how to keep the inductance low, how to make the best thermal flow. Yeah. So you need very good simulation tools, yeah, to make sure that before you build anything, yeah, you have already the right choice, or at least the right direction where you're heading from. Yeah. And that we see really as a big challenge for the future, yeah, that we are ready for these different kind of constructions. We will see to have a scalable platform from low to high power, yeah, in different kind of configurations, two-level and multi-level for the future.
Yeah, in our case, it's mainly inductance, and it's not only the power loop inductance, but also it's very important is the gate loop inductance, especially when you have many dies in parallel in a power module. If each die in parallel has a different gate loop inductance, they switch differently. And we already have, let's say, parametric differences from die to die, and then it's even triggered more to, yeah, it's harder to make a good power module if you have differences in the gate loop inductance for driving. When you want to switch fast, you need to be very low inductive and yeah, to get a full potential. So for us, really inductance, especially gate loop inductance. Yeah.
I would say the main challenges for GaN devices is really to make a complete resyncing, same like you were changing from silicon to silicon carbide. People were always using the same power packages. They want to have a 62 millimeter Icona dual power module, but then you put silicon carbide inside and you wonder it's not working because it's switching too fast. We have too much inductance. So nowadays, when we put GaN in the same kind of packages, it's even faster. And the loop inductance, like Daniel was mentioning, is one of the biggest thing. And on top of it, again, is a lateral device. It's not a vertical device. So the current is flowing on the surface. So you have to really completely resync how to make a layout, how to make the loop inductance, how you make the control pin assignment. This means everything which we were doing so far in standard power modules are basically not usable anymore. And the technology is now evolving for silicon carbide in order to make smaller modules. I think it will be even more involved for gallium nitride in the future in order to adapt to the technology, in order to bring really the inductance down. And therefore, embedded is really a nice solution because this can really enable the complete potential of this technology.
So from my end, I've been funding work in heat dissipation. It's very, very important to increase the thermal conductivity so the package, the module is not a bottleneck. For the low voltage device that are commercially available, as my colleague mentioned, it's really putting many in parallel to get to the power levels that you need in traction inverters and other high power applications. So they're being able to get devices, paralleling devices, make sure they're sharing well, the threshold, they all turn on at the same time. That's the challenge. The second thing where I'm going to be putting a lot of resources is high voltage. I've done a lot of work with different companies like GE, Wolfspeed, and other at 6.5 and 10 kV. And there's a unique challenge there, of course, which is the high voltage isolation, partial discharge. So for the next generation of silicon carbide devices that are coming out, these high voltage issues need to be solved. And of course, in the case of GaN, it can go to very high frequencies, and being able to minimize the inductance is crucial. So that's another area that we'll be working on at Power America.
Okay. Thank you. Do you want to, some of you want to comment about difficulties, challenges in power design, or we go on? Okay. So next point that we want to treat, it's so you talk about die, but then if you go to, so we are looking at the modules, no more at the die, and which are the materials that you think, so I can start talking about molding, but what material do you think will need much more investment in the future? Which is the most important material in the packaging? So I'm talking about copper wire, or I don't know, substrate or molding, the one that should be really focused in the future year to get the best performance for a power module.
I'll let the industry go.
So for us, it's a combination of a lot of parameters which you have to challenge. So of course you will go silicon nitride substrates, you will go sintering technology in order to reduce the thermal stack. But then you have to combine all these kind of additional things, maybe even with internal busbar structures inside the module, and then overmolding. And then you have a lot of different CTEs to manage. And then you have warpage of the materials, of the die itself, of the substrate itself, the mold compound which is taking additional stress. And then you still have to solder or sinter down to a cooler. So all this kind of combination of materials make it very complex to first simulate all these kind of different behaviors, but secondly, all these components has to really to work together so that you have at the end of the day a reliable product. And I think here a lot of efforts from the industry players are made at the moment in order to drive these things forward. And there will be additional technologies coming in this line, whether it's copper wires or whatever other interconnect things. But at the end of the day, thermal mismatch, CTEs, plus the warpage issues, I think these are the critical parameters which you have to master in order to get a reliable product at the end of the day.
Yeah, so just really quickly, with respect to getting to high frequency, the wire bonds that we do in silicon will not work. They're fine for silicon. So I think it's been mentioned before, but eliminating the wire bonds or making them very short, maybe going to a different interconnect would definitely be the way to go, absolutely for GaN and also for silicon carbide as it reaches its high frequency potential.
Yeah, I was about to say a similar thing before you stole the mic. Yeah, it's really coming from how to get the current out of a die. Yeah, so with bond wires, you don't get the full potential. You need to change to other interconnects, cover clip, lead frame, maximize the area on top of the die to get the current out of the die. So to me, this is one of the key figures where we have to put a bit more focus on and to make a reliable product. Yeah.
Beside the material, what has already mentioned, so warpage is a big topic, especially if you want to go sintering for cooler purpose, for example. Yeah, and the second element is the isolation topic. Yeah, especially if you're getting thinner and thinner with the MOSFETs. Yeah, so this is a very, very important topic for the material. Yeah, that you have the isolation solved there and don't get the migration and leakage topics.
Yeah, so as a PCB manufacturer, we love organic materials, so the pre-preg materials and so on. And if you look in the power modules, you find a lot of ceramic substrates. So if we go for isolation to higher voltages, up to 1200 volt, for example, you're somehow limited by the performance of the organic materials. So there are nice materials out there with the increased thermal conductivity, because if you have an organic layer as an insulation layer, it's also a thermal insulation. Therefore, you have to increase the thermal conductivity. So there are materials out there who can achieve 5 watts per meter Kelvin up to 10 watts per meter Kelvin, supposedly. And you can really achieve very low thermal resistances. But to go even further, in the isolation performance to 1700 or even to higher voltages, you would have to increase the thickness. And this trade-off, because on the one side you want to insulate and increase the thickness of the insulating layer. On the other side, you want to be as thin as possible to get the heat out. There will be a certain trend that the insulation for very high voltages, so more than 1,200 volts, will most likely go into ceramic insulations. For the organic improved materials, the supply base is very little. So there are only few material suppliers out there. So the choice of materials for good insulation performance and a good thermal conductivity is limited as of today. So maybe it's improving in the future, but today it's very limited.
Yes, thank you very much. We can discuss about the organic insulation materials. We have more than 25 years field experience using this material, as you know. But from our side, so every material can available. So silver sintering can available, copper wire bonding available, copper metallization also available. But most important point is the cost. Because the power module, the cost requirement is very, very high. And also that from a material supplier point of view, so-called semiconductor packaging, power module, we can have only 10%, less than 10%. Then every material manufacturer, okay, so sounds nice. So power module is a very important product in future. But how much the market? Oh, less than 10%. We cannot provide such kind of material. Then most important point now, cost.
You said that's what I wanted to say also. I think the cost. That also from automotive perspective, I can say the cost is very important. I think we have discussed this morning a little about the cost.
Yeah, this is actually.
No. As I mentioned, the cost is one of the most important things that we have said, and also from performance perspective and the KPI that we have discussed this morning. From our side, not only the performance is important, but also finding solutions that will be enough reliable in par with the performance is much more important. This packaging in the power module, maybe you try to make that one more power density, make that one smaller and smaller. But we like that one actually, as much as that is smaller is better for us, because we have a higher power density, but we have seen when we make that one smaller and smaller, we have a concern about the reliability, lifetime of the power module, and all those stuff. These are the things that we hope we have as a concern. And when you're using the new packages, but we should go further. This is the reason that automotive, or they said, automotive is very conservative. That is completely true. We cannot sacrifice the market, but still it is very important for us to have a very good and reliable solution.
Thank you. So you talk about I'm taking advantage that you talk about thermal dissipation. So the question is, I have two points that you would like you to discuss. So double side cooling, something that we see in the past. Maybe now this year, not many people talk about that. So how do you see that? And since you were talking about taking out the signal, let's say, from a die faster to decrease the interference and so on, what do you think about the heterogeneous integration that has been introduced yesterday morning by TU Delft in the presentation?
Yeah, of course, the heat dissipation is very important. And also that we have some products already used integrated cooling inside of the power module, and also the integrated with base plate with ceramic substrate. Then so that we have some approach for such an integration with the coolant. Yeah, of course, very important. But for me, so the most important point is how to dissipate the heat from top side of the chip. I'm very negative for double side cooling because double side cooling cases that maybe 10 years later or 50 years we have some solutions. But now, so the most the dangerous point can be the chip interface. Then now so chip not only metallization but also the gate oxidization layers. Then today and 5 years we are concentrated on integrated coolant inside of the module. Then next 10 years we have to discuss about double side cooling.
Okay, from the thermal
Wait
dissipation.
a minute. Turn on the mic. You have to put on the switch.
Now better? Loud and clear. So from the thermal dissipation, our technology is supposed to dissipate the heat very, very soon and very fast by using this lead frame technology where the silicon device or the silicon carbide device is directly assembled onto. From my point of view, there are two aspects. First of all, how do you remove the heat and how much heat do you create? First of all, removing the heat is good heat spreading, good heat dissipation to the outside, increasing the size and getting a low thermal resistance, even though you have an insulated area. This can be achieved with these organic materials as of today. So we're coming down to a level where we have ceramic modules as of today, so we can directly compete with them. We are at the same level. And in the future, we will increase the thermal dissipation out of the PCB furthermore by using ceramic substrates inside the PCB. So we will do the insulation not with an organic material anymore, but with a ceramic layer, silicon nitride or aluminum nitride. Depending on which kind of ceramic we will use, the thermal resistance will drop furthermore. The second aspect is if you reduce the switching losses dramatically, then you don't create this excess of heat that you have to remove later on. So in the combination of a good heat removal and in creating less losses, you can achieve a higher power density out of a given semiconductor surface area. So what we have seen, or what was the feedback from our customers, was that we can increase the power of the devices up to 40% in this technology.
Yeah, so many wise words said already. Yeah. I think thermal mass is a quite critical point as well. Yeah, so not just to transport the heat is for sure impossible, but also to give the time to transport it. Yeah, especially if you have some interfaces which are not ready to give it there. Yeah. So that's one aspect, and the other one is really double-sided cooling. Yeah, I understand the concern fully. Yeah, but on the other side, we also see the demand. Yeah. So to a certain degree, we have to overcome this challenge. Yeah. So that's something I believe as engineers as we are, we have to do that.
Yeah, picking up on that, it is super important to have a very good cooling. However, you need to consider all the stresses that the die sees, right? So we had solder material. Solder material is quite soft. So what was the weak point? The die attached. Then we went to sintering. So where's the failure mode now? Bond wires. Now we do topside sintering. And then the stress to the die itself is getting higher and higher, which means there must be new technologies, new metallizations on the die, maybe a different die design. But really from the reliability point of view, it's now getting everything around the die is so robust that now also sometimes the die can be a bit of a concern, especially when it comes to metallizations on top of the die that you need. There, as you know, there are several metal layer stacks, and each metal layer stack is actually then a potential weak point when everything around is stronger and more robust than the metal itself. And there's a lot of papers also discussing about weakness of aluminium on top of a die, and it really comes down. If you have a really robust package and now also the top side, then we trigger different failure modes, and then we need a new development, maybe for a die, to make this more robust for this technology. And
personally, I'm not a big fan of a double-side cooled module. I've seen many approaches when I even was in Wolfspeed 10 years long with silicon carbide products. The complexity to make double-side cooled modules, just from a module point of view, is already very high because you have to parallel 10 dies in one module with filler and gap fillers and so on. But then you have the second point, which is also the cost at the end of the day. You have 2 times the ceramics, and then you still have to do the inverter, which is a complete new vehicle of complexity. So putting all these things together and just to gain later on maybe 15 to 20%, of course you can reduce the cost of the silicon carbide, but you're adding a lot of additional complexity. And from this point of view, I don't believe this is the right way to move. There's a lot of research in this direction, but personally I think the cost adders and the yields which you can achieve when manufacturing a double-side cooled module paired with the complexity of the inverter design, will this technology not make a major mainstream activity? For some activities, yes, but I don't believe this is going to fly.
So I will disagree, saying that I think double-sided cooling is needed, to extract the heat. And as far as the die is concerned, really most of the failures are not the die itself. It's, the wire bonds that connect to the die, the other materials. If you look at short circuit operation, the failure is, the chip will heat up, and then the bonds will disconnect and so on and so forth. Now, in JFET silicon carbides in particular, they've been shown to operate for thousands of hours at 800 degrees. So the metallization is there, the right materials are there, a lot of technology in there. It just comes down to, a big thing that everybody mentioned, and that's cost. What is it that you can do to ensure reliability and ruggedness of the package while keeping within, or the module while keeping within your cost requirements? And that's where we need to see technology advance that will allow us to do that staying within the cost considerations.
From automotive side right now, as I said this morning, we have a supplier. Most of the tier ones that the OEM works, they have a double-side cooling module. And we have seen that the cost of the whole solution, for example, for inverter, they are much lower than us for the power module. Because due to this double-side cooling, even they have the complexity, they have a lower ZTH, and due to this lower ZTH, they can save some chip. As I said this morning, if you save one chip, it's a huge amount of the cost. One chip, when you have, for example, 36 chip, each switch, 8, if you save 1 or 2, we talk about the 300, 400, 500 SEK, $50, $60. Then if I know this complexity that you have mentioned is completely true, but if we cannot go in that way, we cannot be cost competitive.
Okay.
Sorry.
Okay. So let's add maybe one more question, if it's possible, on the time. Maybe we go back to the die, because we did packaging, but the question is again linked to the packaging. So what do you think about hybrid modules? Because, okay, the cost, maybe it comes also from silicon carbide, so why not hybrid? So hybrid in silicon carbide and IGBT inside. So could be a solution, could be an advantage, maybe in terms of cost, maybe will have an impact on the packaging, because actually you integrate 2 different technologies. They both work.
Provided the microphone works. Okay, so that's a very hot topic when it comes to electric vehicles. You have 95% of the driving cycle using about 20% of the silicon carbide power, right? So the question is, you're going to put all that silicon carbide, it's going to be very expensive in order to be able to work at that peak capability for 5% of the time. So people said, okay, let's put about 20%, put silicon carbide to take care of the 20%, which is 95% of the time, and have silicon IGBTs that can turn on when we need the full power to accelerate. So this sounds like a great solution, and the concern there is the complexity of controlling that system. So when it comes to hybrid modules, there's a huge volume application, which is basically electric vehicles. It will bring massive benefits because you can significantly reduce the silicon carbide content by having cheap silicon IGBTs pick up for that 5% of the driving cycle when you need full power. But the question is the complexity, the control complexity that this brings. Is it cost competitive with the full silicon carbide or the full GaN type of solutions? I think that's part of the problem that needs to be solved.
Okay, so I completely agree with Victor. Of course, we have a lot of projects so focused on hybrid module, but so the most important point is controllability. Yes, thank you, Victor. Yes, then we need some special gate driver technology needed for this technology. Then actually, we have some IPMs in the field. Then we are using the HVIC for control. But so this technology, unfortunately, these 25 years, not so much progress. Then we need additional technology focused on HVIC. It's needed for hybrid module.
Okay, so when we started with the embedding technology, we actually started with IGBT components. So in principle, it is possible to also do an embedding of an IGBT component, but there is always a but. The size of these IGBT components are larger, and the thickness is typically thinner. So if you go for copper plating of such IGBT devices, they will start to bow and to bend. This is something that can be overcome, but maybe even more important, I think the combination of a fast switching device and a fast switching package is always making the most sense. And if you have a package which supports fast switching and you put in a slow switching IGBT, this will not lead to the same effect that you can achieve if you use a silicon carbide device. So if there would be a hybrid module, I could imagine that there is an embedding of a silicon carbide and maybe an SMT assembly of an IGBT. Or the first 50% you can save in your application, this is something our customers are considering, is that you use a dual axle drive, and there is one main axle that you drive most of the time, so 90%, as already mentioned, with a silicon carbide. And if you need the full power, then you have a secondary drive where you have an IGBT module inside, because you only need it if you need the full power, and at full power, IGBTs are almost the same in efficiency like the silicon carbide MOSFETs. So it depends how your system architecture will be optimized at the best way from the cost perspective and from a technical perspective.
Just one comment bit versus GaN and SiC. Yeah? So on one side you have a lateral device, on the other side you have a vertical device. Yeah? So that's the combination of both in one package is for a packaging not easy to solve. Yeah, so that I see as a big challenge. Yeah, and on this one we have to work. Nevertheless, yeah, I think you can separate it, but the interesting thing to combine it will remain.
Yeah, I can just pick up on what was already said. So when you put IGBTs and silicon carbide in one power module, it is quite complex. They behave differently. You need to control them. You need to package them. Materials might be different, topside metallization, so the finish on top. It kind of makes sense because, as already told by Thomas, for the peak power, IGBTs can do the job. For the light load condition, silicon carbide is the best. So combining those would make sense. Combining those in a power module is challenging. Maybe it's a better way to separate those and buy a boost axle and a cruise axle. but both in one module is challenging.
I would just add to this one. So it's all about the dynamic behavior of the devices. One is fast, the other one is slow. So the control is really the most crucial point at the end of the day. If you have then a part in the module which is a slow switching device, the other one a fast switching device, you basically need a controller which is mimicking both in a way that they are adapting each other. Otherwise, the system will blow up. Maybe there's techniques in the future in order to make this. I've seen approaches from several players in this field, but I think there's still work to do in this field if we come to this kind of solution. I think from a thinking point of view, it's a practical, good solution. To make it happen, I think maybe it takes some years.
Okay. So we have still 2 minutes.
I have a comment as well. If you look at the certification of the car, we are going through these WLTP cycles. And in the WLTP cycles, 80% of the time, we are in that region that the silicon carbide is more beneficial. It's a lower current range. It means if you look at it from automotive perspective, when you're going to get a certificate that how much efficient is your car, they look at those regions that the silicon carbide is more effective. Otherwise, why we have switched from the silicon carbide, from IGBT to silicon carbide. But still, we have done this test. I think one of the subject that we haven't discussed this morning, we haven't had time, it was that we are going to use, one of the reasons that we are going to go to this system on a chip is to have this possibility to go to the different solutions. We have this flexibility. And when we go to that one, we have enough output, and we need only driver for IGBT's last state for the IGBT and the silicon carbide. It is possible, but as I said, from the certificate, maybe it's not a good solution, maybe it's good. We just use the silicon carbide at that time to show that it works very good. We can design. But we should have, I think from automotive, also cost perspective, if we can reduce the number of the chip, if we use the combination of them, that is possible, then it could be a good solution for us. We are actually working right now, and we are going to define the project regarding that one. That we have this combination power module. We have tested a little, we have simulated, and we have seen the benefits of that one. We are doing that one actually.
Thank you. Thank you. Okay, so we can have some times for question from the audience. Any question?
Okay, thanks. So yeah, thanks for the interesting discussions. So I have one question. So we saw a few months ago Infineon introducing a discrete package device, 2000-volt silicon carbide. How do you perceive this news, and do you see it as a trend? Do you expect it as a trend for other applications to package such die for this voltage class in a discrete package?
Yeah, we saw that as well. To me, it's more for the photovoltaic applications, not really for automotive. The thicker the diode, the higher the voltage class, you also increase losses. Yeah, you have a thicker drift layer, and the 2 kV devices are more focusing on the PV market. Yeah.
So when you fabricate a MOSFET, when you design it, you can tailor its properties to make them specific for the application. So there are MOSFETs that are used in industrial motors. There are MOSFETs that are used in the traction inverter. So in every one of those cases, there's a number of trade-offs in the design. And it just, you understand what your application is, and you design the device to maximize the benefit for the application. With respect to the higher voltage, getting to higher voltages, and I don't want to trivialize things, it's pretty straightforward. You increase, the thickness of the drift layer, you adjust the edge termination, and you can go to high voltage. The real question is is there going to be enough volume in the market for you to go to that level? So as it was mentioned, certainly for PVs, you take the voltage requirement and you give it a 50% overhead, and that's the device that you need. Now, there's a 3.3 kV device. If you use a 3.3 kV device for an application that really can do with 2.2 or 2.5, then your conduction losses, become high for no reason. So yes, I think that we will see a lot of customization, and it's not a difficult thing to do if you understand how to design the device, but the requirement is for the market volume to be there for somebody to make that investment and make those devices.
Okay, so the 2.5 or 2.0 kV silicon carbide device is a hot topic. So as Ulf Speed said, mainly they focus on PV application, especially central inverter systems. But not only PV, but also the charging station. This morning, from Warsaw University made the presentation. So now the DC catenary going up from 1,000 to 1,500 volt system. For this application, this morning he made the presentation, utilized the 3-level topologies. But we want to use the 2-level topologies. For this, 1.7 kV device is not enough, but 3.3 kV devices loss is very high. Then recently everyone rushed into 2.0 or 2.3, 2.5 devices. It's a very promising application and a promising market, I think.
I think we should think about that we can go to any level of the voltage due to the benefits, but we should think about also side effect of that one. When we talk about the higher voltage, you should think about a higher clearance and creepage, how we should design the bus bars, how we should design other components inside the system. It is good to have, but it is fully new challenge. We go to another range of the standard, the IEC standard. We have completely different requirements inside the system. Even we have the devices. As I mentioned this morning, this is a system. This is not only device or power module that is worth 2 kilovolt, 3 kilovolt, 5 kilovolt. When we go to 5 kilovolt, then you need to upgrade everything. And the inverter in this size that we have a power, we like a power density higher. The power than the inverter in this size. This is not the case. I think it's not so easy just to see the component.
So one more question, if
just really fast. I wanted to say that the device is the engine, right? But then you need the rest of the vehicle. So if you take basically a silicon carbide device and you put it in a silicon circuit, it's like taking a Ferrari engine and putting in a little Volkswagen, right? So absolutely true. It's not just the device to get you to the higher voltage, but you need all the accompanying module and system considerations that will increases the cost. So that's why it's very important to have the right volume in the application to make it worthwhile for people to do that.
yes.
What's the panel's view on that 400 volt announcement of Infineon silicon carbide MOSFET from business point of view? Because it's now the other end from the last question. And, we're encroaching into the silicon GaN territory also.
I think there's one famous application for 400 volt. This is audio. So this is a long story already since a long time, and you just need 400 volt for audio application.
How about the DC to DC inverter running a high frequency?
Maybe our friends from Wide-Bandgap can answer.
Yeah, let's see. Yeah, of course, the lower the device voltage, the faster it can switch. Yeah, so you can optimize a die to a certain application. We also have seen that the demand was so high, and partially, if you don't get the devices for the business case you have, you may have to step back a bit and take what is available in the market. Yeah, so maybe then go to a bit lower power cars. Yeah, maybe run a few more years on a 400-volt bus. Yeah, so there are different aspects to it.
I hate to interrupt such an exciting and beautiful panel discussion and panel experts. Maybe we could allow just one, because we have to make change in the program. I will announce it right soon. But maybe is there anybody else in the audience who is really eager to ask the question? So last chance.
Okay, welcome back from coffee break. Congratulations on making it to the final session. Great. It's also a very important one because it has to do with packaging. We heard a lot about packaging these 2 days. So the first speaker, I would like to introduce Dieter Elisabeth from ISiCPEAW, and he will talk about GaN power devices and power modules.
Thank you very much, Klaus. So it's time to wake up. Last session is starting. I will give you some overview about GaN for high-power traction inverters. That's the focus of our activity at ISiCPEAW. And I will just give you a journey where we have started and where we want to be over the next couple of years. ISiCPEAW, just as a glance, we are a startup company out of Israel, fabless, with TSMC as a foundry. We have around 55 employees, and we're operating out of Israel and have offices in the US for packaging. And then in Austria, we just opened last year our operation and also have an office in Shanghai. So we will talk here today about our D3 GaN technology, which is a direct drive GaN, D-mode, as a cost-effective solution in order to replace silicon and silicon carbide in the electric drive inverter. We have demonstrated a 2.2 milliohm 650 volt half-bridge module using 4 times our 8 milliohm devices in parallel. So paralleling is also a big topic here. And we were going to a dyno in order to see is GaN really viable in an EV inverter environment. So not just making theoretical exercises, but also make a real dyno testing. And what we are converting now is to use this technology and bring it into a transfer molded, highly compact module so that we can utilize the technology in the future for high volume applications in electric drivetrain. So GaN is not GaN. That's the basic, first of all. There's so many different GaN products. We have seen yesterday already E-mode, D-mode. You have direct drive. You have cascoded devices. So we have also a normally on device. Therefore, we need a low voltage MOSFET. The difference to a standard classical cascode is that we are switching just the PMOS on one time. And then we are switching the GaN device so that we are not introducing any reverse recovery loss of the PMOS. And when we are at the exit, then we are switching off the PMOSFET. So that's a difference to a classical cascode. In order to do this, we have a very simple gate drive circuitry, which is enabling us with an 11-volt undervoltage lockout circuitry, that the circuitry is enabling the PMOSFET. And then we can switch the device on and off and still having the blocking voltage of 650 volt. And the benefit of having a D-mode GaN is really that we have a very high threshold voltage above 7 volt. That's the beauty compared to an E-mode, which has a very low threshold voltage and which is makes it very vulnerable for inductive switching applications. So our generation 1 was a 7.78 milliohm in simulation, and when we manufactured the device over the last 2-3 years, we were really around this kind of boundary in a very narrow area. So we have plus minus 10-15% spread, so not like in silicon carbide where you have a 20-30% spread of RDS on, so we will have a very narrow spread. Our Gen 1 Plus, which we have just gotten beginning of the year, is now at 5.8 milliohm, very similar to the ISiCPEAW device, which was shown yesterday. And also here, the simulation was basically taking us to the results of our device. And these we have now in volume production, and we are utilizing this one as well in order to increase the power density for the power modules. As we have learned before, we have to parallel also devices. This is around 150 amps, similar to the ISiCPEAW device, and we can just parallel them in order to bring it to power modules. One major difference between gallium nitride and silicon carbide, it's a lateral device. So the current is really flowing on the surface. So whatever you know about power modules, structures, layout, and so on, forget everything because you have to start at zero because current is flowing lateral. So you don't have a vertical device here. So we were starting on the right side with our Gen 1, the VO8, and we were using standard wire bonds just in order to demonstrate it's viable, it's doable, it's possible to integrate. But now we are changing also the methodology. So we take at the surface, we take now source, drain, in order to reduce, first of all, the RDS on of the device, but also increase the ampacity of the device. So with the same chip size, we basically get around 35-40% more current out of the same cell structure. So even we are not changing the design of the chip itself from the cell structure, just by redoing the RDL layer and redoing the organization on the surface of the device, we can improve the device properties by more than 30%. And we were introducing also aluminum ribbon bond in order to increase ampacity, because the wire bonds, first of all, are not good for reliability, and it's also having a very high resistance at the end of the day. So we were choosing aluminum ribbon bond here in order to improve also reliability of the module. Paralleling of devices is an issue, and basically you should do really best practice like you do with silicon carbide or other fast switching devices. So you need balancing gate resistors, which are either, let's say, discrete mounted, depending on your layout. This is just one example where you can reduce the inductance, especially also the gate loop inductance. Therefore, we are mounting 2 pins here in order to reduce the Kelvin and the gate reduction of the pins, and to facilitate that you can really fast switch the device. Later we will be able to remove this balancing gate resistor, similar to what silicon carbide was doing, and move this inside the chip itself. This is with our next generation, where we are doing the integration of the gate resistor into the device itself. So what we have done as a first iteration in order to demonstrate the viability of the technology, it's a kind of, let's say, looks like an iconodual from the outside, but it's not a real iconodual, because we are using our discrete devices, which are using aluminum nitride substrate inside, and we pre-pack it together with our gate driver board in order to have a very compact design, and then put also capacitors on it in order to make it very low inductance. So by achieving this kind of mounting technology, it looks like a power module. In reality, it's not a power module. But what it does is it reduces the capacitance and the inductance of the system. So by putting this, where's the laser pointer? Not really. Here. So we are basically canceling the fields out here, because we are doing this multi-level of the shieldings. And with this one, we achieve, even with this very old style looking of a conodual, we come to a 3.9 nanohenry, which is really needed in order to make fast switching devices at the end of the day. And this is where we were showcasing you need a low inductance module in order to unlock the performance of gallium nitride. One important point was paralleling of the devices. So now you're using 4 times pre-packed of devices, but they all have different properties. And we are not binning our devices. So as showed you before, we have already a very narrow range of RDS on spread due to processing issues. But also the threshold voltage spread is also very narrow. And we are not binning the devices. And then we were measuring how much deviation we have really with turn on, turn off between the different devices. And this is roughly 2.8 nanosecond of a delta T between worst performing and best performing part. This means at the end of the day, all the switches are switching on at the same time. So this means you need a low inductance packaging on the one side, you need capacitors, and then you can control even 4 devices in parallel with this kind of approach. No. So why we are doing this, at the end of the day, the OEMs, tier ones, they all want to say, yeah, GaN is fine, but demonstrate that it's really working. So as a small startup company, we really had to do the heavy lifting from manufacturing a die, put it into a package, put it in a power module, making the control, and bring everything to an OEM to run it on a dyno. So for a small company, this is heavy lifting, but we made it last year, and we were testing with the WLTC standard more than 100 kilowatt with this kind of setup. So the last year's testing was this early, where is it here? This field area. So we were not going in field weakening or let's say very high current. I show you later where we are at the moment. But unfortunately, the test for full WLTC should have been done last week, but the OEM delayed it to next week. So I couldn't show it this time, but maybe after this audience, we can distribute it later on with all the results out of this one. So we were testing it up to 230, 40 amps in the WLTC testing and get a complete map out of this one. And we achieved roughly the same efficiency like a silicon carbide inverter. Theoretically, yes, you could be even better because you don't have a QRR, you don't have a body diode. So there's a lot of optimization still doable with this kind of setup. But it was a kind of first testing to show, yes, it's workable in the inverter environment. It can withstand the very high inductive load which you are getting as a feedback to the gate so that you're not destroying the devices. And under this condition, we were happy with the results that we can run this in this limited operation. Then we were even going higher with the test forms. So this was the first testing. Then we did the second testing. And we were now with up to 350 amps. So we extended the range up to 350 amps. And we're going with 110 kilowatt. One important factor is gate robustness. So gate robustness is a key point for D mode versus E mode. And you will have a very high spike on the gate, very similar to IGBT switching, silicon carbide switching. And that's the reason why most of the E modes are failing under this operation. Let's skip this one. So what's the next evolution? So what we're doing now is basically taking our applied learning and bring it into new overmolded modules. And also here we are going for 3.2 nanohenry, which is really needed in order to unlock the potential of gallium nitride. And we want to use here basically same technique like with conventional modules, which we are using sintering technology, normal die attach, aluminum ribbon bonding, and so on. Okay. Now it's coming. So we are basically here in this evolution. We are now releasing this kind of building block for PCIM. So first time to show this outside. It's a kind of overmolded module as well. And then we were even working with some of our partners here, with Schweizer Vitescu, on embedded technology as well. So as people have already said, at the panel, you need copper on the surface in order to make it happen. So this is something which is going on. So let's skip this one here. So from the interconnection, it looks very similar to whatever you do with standard products. You just do die attach, sintering, and then you connect the pins and terminals. Maybe two things about materials. We were also testing transfer liquid pressure sintering because we have a piezoelectric device. And from this point of view, we were trying to use a non-pressure material, which is TLPS. We saw some cracks. We will still investigate this one. And we were doing also silver sintering for this device. And even with 5, 10, 15, 20 megapascal, we have not seen any crack on the devices or change of parameter. And we did even power cycling measurement here. So just as a device roadmap where we are now here. This one I showed. This is the next one, which was just coming out of fab with 4.7 milliohm. And we are now working with a 2.5 milliohm in the same chip size, which is coming before end of the year. And this will enable us to make in the same power module form factor, which we have now 300 amps, go to 400 amps, and then even above 500 amps in the same form factor, so that we are basically can replace silicon carbide directly with gallium nitride in the same form factor. So, conclusion, we have shown with our Gen 1, it's viable to do it. We're now emerging into Gen 1 Plus, Gen 2, Gen 2 Plus over the next 12 months. And we will demonstrate this in full WLTC cycle and develop the complete final assembly stack for high volume production D3 GaN power module. Thank you.
Time for one quick question. I think you were.
Can you show where physically is your? Can you show where physically is your silicon MOSFET parallel, the second part of the cascode?
What do you mean? This where?
You have a silicon safety MOSFET switch. Where is physically sitting in the same?
It's in the same power module.
In the same power
yes.
module. Okay. Yeah.
Okay. Thank you. I think we will move on so that we can keep the time, people leaving. If you're looking at the schedule and if you're confused, the Mitsubishi talk has moved to the end. So the next speaker will be Thomas Gottwald from Schweizer, and he will talk about embedding of silicon carbide MOSFET into a PCB. Please.
And as soon as we see the presentation, I can begin. Okay, it's there. Okay, first of all, I want to show you an outline of the talk, but it's not here. Don't mind. I want to highlight, first of all, the technology that we use for embedding. As mentioned earlier in the panel discussion, we are not using bare die embedding, but we're using an embedded component consisting of a lead frame with a cavity on the top side, and inside the cavity we have the power semiconductor. This brings all the three contacts to one common level. That means the drain contact is represented by the lead frame, and therefore here at the top you see a cross-section through such an embedded device, and therefore the drain contact can be taken from the lead frame side. What you see here is the standard cell with the embedded device inside, and from the top side you see how we do the interconnection between the device and the PCB. It's done by laser drilling onto the contacts of the component. Here you see the source contact, here you have the gate contact, and here you have the drain. So what you see here is a half-bridge design. So the connection is done from the drain to the source directly. So this would be your phase contact point. What you also can see is that at the bottom of the standard cell, during the production, we implemented 2 levels of copper-filled microvias. The reason for that is to improve the thermal conductivity from the device to the outside world. So when we started, the main driver of embedding was miniaturization, because these power electronic components at the surface, they're taking a lot of area, and everybody wants to get rid of them or get more functionality in the same space. And still, miniaturization is one of the drivers, because everybody's trying to increase the power density for his application. But what we also learned is that we can achieve higher efficiency in switching. This is because we have a very fast switching. That means that we are passing through the transients much faster, where we create the losses. And therefore, we can increase the efficiency tremendously. We also see most asked question, what about the reliability? For power electronic components, one of the most stressful tests is the power cycling test. And if we do that, normal power modules are tested at a delta T of 80 kelvins. If you do this with such a P-square pack, you will test it forever, because you don't see any failure. We tested more than 2 million cycles and we had to stop the tests because we didn't see anything. We had to increase the delta T during the testing to provoke any failures. We went up to 120 kelvins delta T, and after 1.5 million cycles, we did not even see failures. Only when we went up to 150 kelvins, then we have seen failures after approximately 150,000 cycles. Try this with a power module, and you will have first failures after 5,000 or 10,000 cycles. So, and kind of a surprise, if you're inside a PCB, you would expect that it's a problem to get the heat out, but we found that we even can surpass the thermal conductivity of power modules. So latest results from one of our customers was a module thermal resistance of 0.1 kelvins per watt with 4 components in parallel. So for the individual cell, you have approximately 0.4 kelvins per watt, even though it's insulated. And it's lower if it's not insulated. So there are some preconditions that we need. We talked about this in the panel session already. First of all, you need to have the power semiconductors in the right configuration. That means we have to have copper terminals on the top side, and on the back side, the surface must be suitable for either silver sintering or for diffusion soldering, because we want to remain the component to stay flat in the cavity. Otherwise, this would lead to differences in the height or in the depths of these microvias, which then would be much harder to plate and maybe even less reliable. So this is the technology as a short glimpse. Here's the outline that I missed. So let's have a look at the value chain, because the value chain, first of all, is changing a little bit. And secondly, it was hard to establish this value chain, maybe even harder to establish the technology at all. So first of all, we need to have the chip in the right configuration. This is coming from a semiconductor vendor for sure. But then what we want to achieve is this so-called standard cell. And therefore, we most likely want to see the semiconductor manufacturer in the role of a component manufacturer. So this is somehow a discrete component which is used for embedding. So the lead frame and the die attach should be carried out by the semiconductor manufacturer. If he's unable to do so, we will establish OZ companies and bring them into a position that they can produce the standard cells for us for a wide range of suppliers of silicon carbide manufacturers. So this is an important step to have such an embedded component. First of all, you need to do the die attach, then the singulation, and then the test. The test is one of the most important points of this component because a fully functional test is very easy to perform or to carry out if you have a discrete device. On a bare die, you cannot have a fully functional test with a full current. And there are still some components failing after the first switching on, even though they are functionally tested on wafer level as good components. And this would lead to early failures in the embedding. And therefore, this test is crucial because we make sure that we work with known good devices or known good standard cells. So we start only with good components into the embedding process. So then we take these components and put them into the PCB, do a lamination process and embed them. That's the power stage. And this power stage is again taken into another PCB, another lamination process where we implement two additional layers on the top side to make it intelligent, the power module. That means you can add the gate drive circuitry or even the full control circuitry and come up with a single board inverter, for example. So we have two products in series production right now, and both of them are single board inverters with 12 of those standard components inside. So we created, meanwhile, kind of a portfolio for P-square packs, different types of. What you see at the top is what we are doing exclusively with Infineon at the low voltage level. What you see here is that underneath these standard cells, we have these two levels of copper-filled microvias to dissipate the heat optimal to the outside. So it is a non-insulated buildup. That means the drain potential is at the backside of the P-square pack. But this doesn't play a crucial role because in the assembly process, our customers take a thermal interface material which takes over also the insulation of the system. So in that case, the combination of non-insulated P-square pack and insulation with a thermal interface material led to the best thermal resistance. The second generation, which is in series development right now, is supposed to go into 400 and 800 volt electrical system applications, so major drive applications for the automotive industry. And this is an insulated version. And this insulation is maintained by just leaving out one of these layers of copper-filled microvias. So we're using organic materials as insulation materials, and if you do not penetrate them, they are still insulating. These materials are special materials with an improved thermal conductivity to bring down the thermal resistance as good as possible. But if you do so, now I somehow jumped out. I'm sorry for that. So if you do this insulation, it is not only an electrical insulation, it's also somehow a thermal insulation you don't want to see in your system. And that was the reason. Still, you can achieve low thermal RTH, so this works pretty good. But that was the reason why we said we want to further improve the system. And now we talk about the generation 3, which is actually a ceramic P-square pack, or in short terms, CP square pack. Today in the generation 1 and 2, we use just a copper lead frame. That means it's just a copper block, massive, with a cavity, and the power semiconductor is inside the cavity. And this will be replaced by a ceramic substrate. Also a ceramic substrate with heavy copper layers on the top side and at the bottom side. So at the top side, we also create this cavity, bring in the die. So from the outline, it's pretty similar to this one, but the ceramic insulation is already in the level of the standard cell. And as the ceramic has got a much higher thermal conductivity, the thermal resistance will drop tremendously, which I will point out with the next slides. So the status of our generation 1 is we are since 2022 in mass production. So series are running. We're scaling up now from 2 factories. Right now we have two large projects, a P0 and a P2 architecture for starter generators. And we use this configuration. So what you see here is the inner layer with the opening, the standard cell with the die inside. We have one heavy copper layer at the top, a heavy copper layer at the bottom, and we have a logic layer at the top, and we have another layer at the bottom for symmetry reasons. So the total thermal resistance from the junction to the outside, so somehow junction to case, is in the range of 0.2 kelvins per watt per die. If you do parallelizing, the module resistance will drop. But if you now go for insulated version, you see what happens. The thermal resistance is jumping up to more than the double of this value. Even though we are using materials which are heavily filled with ceramic material, so the thermal conductivity is 5.5 watt per meter Kelvin. Still, with this thermal resistance, you can achieve very nice module resistances. One of our customers had 4 devices in parallel, and the module resistance was 0.1 Kelvin per watt. So it is really suitable for most applications as of today, but still it could be improved. So we are in series development with this technology, and it's supposed to go into drive inverters, 400 and 800 volt, as well as DC converters, onboard and offboard charging. Then the generation 3, according to our simulations, you see we have now the insulation already in the standard cell with a very high thermal conductivity from silicon nitride or aluminum nitride. And with silicon nitride, you would come down to 0.2 kelvins per watt again, like in a non-insulated version, which drops tremendously, which is almost half of the insulation. And still, you have already an insulation built inside. And this is supposed to go into the very high power density drive inverters, 400 and 800 volts. So if we look at the roadmap, then we can see we are in mass production with the generation 1. We are in series development with the generation 2. And we are still in pre-development with the generation 3. And I have to speed up because I only have 5 minutes left. So I will show you some results that we achieved in this technology, which are pretty nice. So we have been talking about double-sided cooling. We already did one of the applications for one of our development partners, Virginia Tech in the US, where we used double-sided cooling. Due to the double-sided cooling, the thermal resistance went down to 0.24 kelvins per watt. But what is a very nice result is that the stray inductance in this sample was less than 1 nanohenry. It's 0.744 nanohenries. And we could switch very, very fast with 70 volts per nanoseconds. And while switching this fast, the overshoot voltage was very little. It was less than 50 volts. And the following diagram points out this measurement. What you can see here, the rise time was approximately 70 volt per nanosecond, and here the overshoot voltage and the very, very little ringing after the switching. So very, very smooth switching. If you're interested in this paper, you can get it from us. So this paper showed that you could use 900 volt devices for 800 volt electrical systems. So you could make use of a lower RDS on. So efficiency increase, where does it come from? First of all, everybody turns his back to the IGBT components because they're switching slow. And the first measure is to replace the IGBT components by silicon carbide, and you win the first 80% in switching losses. But what happens if you go to embedding with the silicon carbide components? Just keep in mind, in the module, you still create 2.6 millijoules per switching sequence. And we made the same measurements together with Infineon, and we found, even though the gate resistance was at 10 ohm, we switched not as fast as we could with 28 volt per nanosecond. The switching loss was 0.86. So if you look at the equation here, you can see you can save approximately 65% of the switching losses compared to silicon carbide in a module. And therefore, you now have a summary of the competitive advantages that you find. One of our customers makes his own modules, and it is a comparison with a pretty new module, which is coming this year to the market. They have a thermal resistance of 0.7 kelvins per watt per die. And in our P-square pack generation 2, so organically insulated, it was only less than 0.5. Switching speed was limited to 20 volts per nanosecond with a module. We achieved up to 100 volts per nanosecond with the embedding. And the stray inductance at this module was 8 nanohenry, while we are in the range of below 1, up to maybe 2 nanohenries, if there is not so much design experience. A very interesting figure is this one. The current density that you can drive across the component was limited to 3.7 amps per square millimeter in the module, but 5.3 amps per square millimeter device surface area, which is 40% more in the embedded. This is coming from creating less losses and dissipating it better than a module does. So in terms of power density, if you put the module to 100%, our customer achieved 190% power density with the embedding construction. So this brings me to the summary. I showed you that you can achieve a high power density inverter with much more than 100 kilowatts per liter. We have very low switching loss and very low stray inductances in the commutation loop, and we see very low total losses in operation. So we have a very high reliability as well in passive and in active power cycling, and there is a very low thermal resistance of 0.2 to 0.4 per die, and we already have an automotive series production running from 2 locations, one in Germany, the other one in China. So we think this is a nice new technology, high performance technology for automotive traction and inverters and other applications. Now you made it.
Thank you very much for that interesting talk. We have time for a couple of questions. Wait.
19.33 minutes.
Yeah. The question about this ceramic layer that you're going to add, which technology you're going to use on the surface of the ceramic to connect that onto the copper? And do you think that is enough reliable?
You mean for the die attach?
No, die attach. I think die you're connecting to this lead frame, copper lead frame, and then copper lead frame is going to connect it to this ceramic, and also ceramic is going to connect it again to this I can say copper block, and then goes to the other embedded technology. How you're going to connect? Which technology you're going to use in that one?
I'm not sure whether I grabbed the question correctly. So do you think, how do we connect the P-square pack to the heatsink, or how do we connect the die to the lead frame?
To the ceramic to the lead frame.
So actually in this generation 3, the ceramic is the lead frame. And we are doing an assembly of the die into the cavity of the ceramic. And then we are placing this standard cell, ceramic standard cell inside the PCB. And then we do the interconnection the same way like we do it in generation 2. That means drilling microvias to the contacts of the device and to the contacts of the copper surrounding the device. And maybe we need to have the picture. So here we are.
Between yellow and the orange ones. I suppose that this is the technology on the top is the same technology.
So this is a substrate you can buy from the market. So this is a double-sided copper coated ceramic substrate. So you can purchase this from the market. And what we do is creating this cavity and doing the die assembly in the cavity. And then place it inside an opening of the inner layer and doing a lamination process of the next layers and doing the interconnection with the microvias from the top and from the bottom.
Due to the height, this is enough reliable due to the different CTE that you have, or?
We're right now in the first feasibility studies. So the first samples are ready today and not yesterday. So now reliability tests will be the next step.
Thank you.
Second question.
Same picture, please. In a little bit higher voltage, like 1200 volt, the vertical insulation along the ceramic would not suffice in classical views. How do you assure that the insulation distance is around into your organics?
So if you use a thickness of 250 microns here, you also have an insulation distance of 250 microns through the resin, which is covering the standard cell. So with 250 microns, you can have a very high blocking voltage. So the typical material property is 40 kilovolts per millimeter. That means you are in the range of 10 kilovolts. With a 250 microns insulation distance.
Did you do reverse bias testing on this?
Excuse me?
Reverse bias testing.
SPICE. No, we did not do SPICE testing.
Bias.
Reverse bias.
Reverse biased.
Yeah.
Not yet. Not yet.
Okay. No more questions. I have maybe one very quick question. Have you tested it in humidity?
Yes. So H3TRE is one of the standard tests that we carry out with our generation 2. Yeah. Not with the generation 3 yet, but the construction is pretty similar. Yeah. And according to our tests, it is not 100% up to now. And we're looking deeper into it. But we see that from 100 devices, there are only few failures, which we suppose are coming from that is a kind of a lab process up to now, manual manufacturing process, and we see from the 97% good devices that in principle it works.
Okay.
Sorry, at which voltage?
At which voltage? 1000 volt.
Okay, I think we thank you. Thank the speaker again. Move on. Next speaker is Michael Gössler from AT&S, and he will talk about under the surface embedding for automotive and industrial applications. Please go ahead.
Thank you very much. Thanks a lot for the presentation. I think what I will do in this presentation is also to cover the differences between the two embedding technologies, because basically what we see also between the two technologies, the benefits what we see, they are quite similar, but I will show you. But before we start, actually, I have one teaser. So actually, I have a good friend at the Austrian Power Grid, and he now introduced me to this model from the power grid suppliers, that they will do a dynamic pricing, based on the daytime when you charge your car, when you use your whole energy, And actually, that's a very smart idea. And my neighbors who invested a lot in PV, they are already now thinking, why should I spend all my money to put into the energy systems? So one very nice idea they have is to use the EV car, especially the second one from the wife, which stays at home. And with the bi-directional switch, they can charge and overcome this situation, and not invest a lot of money for the PV systems with the batteries at home. And I think you can see here the automotive and the industrial business both are growing together, and we have to use all these things in a very smart way, to overcome the critical energy situation for the future. And that's something I think what we have to keep in mind. On the other way around, once per week they go to the company and charge their car as well, and then they put it again to the system at home. Also smart, but maybe illegal. Good. Just a few slides about AT&S. I will not bother you too much with this one. AT&S has around 1.8 billion revenue. We are one of the big companies for PCB and substrate manufacturing with different locations worldwide with approximately 40,000 employees and 6 plants. Here you see we have currently 3 manufacturing sites where we are capable for embedding. So one is the Leoben, the Austrian facility where I'm also located. There we have installed clean room requirements, everything to ensure that we can produce this type of boards. And the same is valid for the Chongqing side and for the Shanghai side. Especially if we talk about EV, China development, China will be a major role in the future there. So we also need the production locations there. One thing what also came up yesterday is back-end packaging technology. And AT&S has invested in Europe around 500 million euro in a new facility for R&D and small manufacturing capabilities. So around 500 people. And the main thing here is why I also want to show you this is we have now clean room areas. Pretty new standard. For all the developments and also further prototype lines. This is very crucial, especially if we are talking about high voltage. We have bare dies in the line, and every dust particle you typically find in a PCB manufacturing floor can destroy your reliability. So that is a key requirement what we see. Cleanliness is everything. Without cleanliness, we don't need to handle bare dies. So, as said yesterday, there is a backlog in packaging technology, but we have done something in Europe. We also believe in Europe. And if you need something, we are ready to do this. So, AT&S has actually a quite long history with embedding. So, we started in the year 2000 approximately with our first samples, which were trimmed resistors and capacitors. In 2012, we had the first mass volume product. This is a DC-DC from DI, low voltage, which we produced now in the meantime are several 100 million pieces on the market. And what is quite exciting is it's still running. So there is no other way to produce this package more efficient. That's the only reason why it still exists. 2018, we did the first mass volume qualification for the GaN packages, either 100 and 600 volt. I have also a second slide on this one. And this is now also running in mass volume. And now our next target for 2025 is the basic qualification for mass volume. Just to give you a glimpse about the GaN package, it's a 2-layer device. 500 micrometer thick only, with laser microwires on both sides, as we have seen, and qualified up to 650 volt. So where do we see the big benefits from embedding versus all the other packaging technologies? And that's quite important. One thing what we can easily do is to make design changes. It's a PCB. If you want to change a design, it's one single layer. You just change the mask, or even with LDI, it's even easier. So it's not similar to standard packages on the market, where this is quite tricky to handle, or also including then NRE cost for changes. So as everyone in the automotive industry is now developing its own module, we see this is a big benefit because we can really be flexible. Just important, we will do all the delta qualifications for the design rules according to the voltage levels, voltage and current. And then you can apply this from a half bridge to a full bridge for whatever configuration you need. You have all the design flexibility for the modules you need to change or create, and this gives us a lot of benefits. We are also quite fast in prototyping. 6 months is mainly now also about availability of dies. As also Schmeitzer mentioned, this is a critical issue. And we also see still miniaturization as a clear trend, also based on the power density. Advantages, already mentioned, the loop inductance for sure is one of the key things, but that is very similar in both technologies. Materials up to 200 degrees Celsius. even more is feasible. We have ultra-low CTE materials, which fits the CTE of the die itself, which is also quite important to ensure the reliability of the module. And insulation. Here I made a very, I would say, common approach where we compare the two, a standard technology with a new one. So the key elements are for sure, we can switch faster, we reduce the inductance, yeah, and as I've shown in the noontime, yeah, the thermal resistance we believe can be either be done by a thermal pre-break or by a DBC. This is now just depending on what you need from the application. One point here, NRE cost. Yeah. So we see maybe we are not capable to reduce significantly the price for the package, but we can reduce the NRE cost. Yeah. And that should help us tremendously also to ramp up and scale up the capabilities and the volumes for further growth in the EV business. Because there is a lot of volume in PCB manufacturing which is available. Yeah. So if we can utilize, if we don't have to invest significantly in new lines, this will help us to keep the NRE cost low and really scale the manufacturing. So what is now the difference actually between us and Schweitzer? What you can see here is the BASIC approach. So BASIC means we have a planar surface component integration. So the die on the bottom side is flat and fully connected. So that's a main difference, what you have seen before. There we have the laser microwires on the bottom side. Here we have the full side and the full area of the die on the back side available for cooling. On the right-hand side, you can see which is then the cell. So we have the low side and the high side and the connection by the vias. In the cross-section, you can see the die and the laser microwires connected to the die. Top side, laser microwire interconnection is the same thing. What is also a difference between us is we are not working with a lead frame, we are working with the bare die. Means we can buy standard components and we don't, I wouldn't say we don't care about the components, yeah, but we are flexible from the supply chain. 1.1 up to 10 times is approximately the value we can use. Yeah? From the die thickness, we are now at 110 micrometer. What is the latest generation of SiC dies approximately? And also one big benefit we see is the gate dimension. So we can go up to 300 micro, in the future also down to 250 micrometer, which gives us more area for the source as well. Also important, we only use dies which are KGD tested, and we use tape and reel manufacturing. So no one is touching any die in our manufacturing lines. It's a fully automated process from sintering to assembly. That's quite important to keep the reliability high. So one of the big issues we were facing also is how to create thick copper structures without plating. Because plating is a quite inefficient process. Yeah? To plate 200, 300, 400 micrometer copper is a quite time-consuming process, yeah? And not efficient. So we thought, what's the best interconnection way and what is already available on the market as well? So we decided to go into sintering processes to connect the thick copper structures to carry the current, yeah, with the BASIC approach in the center. So the center core, the BASIC core will always stay the same, and then you do the interconnection via sintering. Also important, we will do the sintering process during our relamination process. So what's the benefit of this? It's two elements. Yeah. Low pressure on the die, and we have a lot of time. We will anyway laminate 2 to 3 hours in our pre-break configurations here. So we can give the silver all the time that it needs, yeah? And that is a big benefit. And the second thing is we save cost, because the same thing when we do the lamination, we can also do the sintering together. So we have also done here more than 300,000 power cycles with a delta T of 100K. And as you can see also from the structure, it looks quite good. This I've shown also today already. So here you can see the standard cell in the middle, which is the BASIC approach. And then we have one core on the top side, one core on the bottom side, which allows you to carry the current on one side, but also allows you to do the cooling. And there we are already, we can do single-sided cooling. We can also do double-sided cooling. Yeah? The benefit with this construction is that you have from the symmetry of the stack up quite good values. Yeah? So you're not significantly different, which creates a lot of warpage. Yeah? So with the symmetry, there comes also the reliability. For sure, on the bottom side, that's the big challenge for the isolation, as already mentioned as well. So thermal prepreg is one solution. Sintering, difficult. Risk. So that's something we have to keep in mind, yeah? Especially also for mass volume. So therefore, we're also thinking DBC is, for some solutions, also a way to go. Yeah? It will not be necessary for every application, yeah? But for some applications, we believe that the DBC or similar materials than a DBC makes sense. Last important step here. So on the bottom side of the die, some years ago, we always needed double-sided copper, which is not available for SiC dies. So in the meantime, we can also work with all standard interfaces on the bottom side of the die, which gives us the availability to use standard dies from the market, more or less standard. So what do we do to ensure that the board is working? We can test actually different things. Yeah? We can test the die, the incoming die, we can test on panel level, and we can test at the end of the process. So always in panel format. So, and our panel format is 600 times 400 in a size. So that's also different to the typical module business. Yeah? We have much bigger sizes, which helps us to improve the efficiency. Reliability. That's now the key element, yeah? And everyone is already laughing, yeah? As already mentioned as well, yeah, power cycling is not one of the critical tests. The critical test for this type of modules is humidity, temperature. Yeah? So there, and the voltage for sure. Yeah? So that's the key elements. So we have these standard tests in-house. We also did already tests. The tests are also ongoing. Yeah? We are now somehow between 3,000 to 4,000 cycles, yeah? And we see quite good tests, yeah? Results. So we have the HTRB 10 modules. It's a half-bridge configuration tested up to 1,000 volt. And you can see we had the first failure on the high side on one module at 1,800 hours. We had this first defect on another module at 2,300 hours, yeah? Which is already quite promising from the result. And the test is still going. High temperature gate bias, also 10 modules. Yeah. Here, first failure at 1,000 hours, second failure at 1,600 hours. High humidity, high temperature reverse bias, yeah, up to 1,400 hours. Yeah. One failure at around 1,000 hours, yeah, and still running. And then TCT, we had one failure at around 1,000 cycles and the second one at 2,000 cycles. And the test is still ongoing, so we will see. We will run up to 5,000 cycles. I hope we will get some failures, to be honest, because otherwise I cannot create any viable analysis. Yeah? And for sure, it's also then the failure analysis, what we see from the first failures, which help us. Yeah? And we have to do much more here. Yeah? And it's not so easy because every customer also wants to have his specific design. They don't want to share anything. Yeah? So we created this one, but for every module, we also have to do and repeat this kind of testing. That's a key element for the future. Good. Any questions?
Thank you so much. Yeah, we have time for questions. Guess who?
RTH, range of the RTH.
Sorry?
Range of the RTH, ZTH maybe it's better to say. With this technology, I've seen that one of the slides you had shown that you have put also, I've seen gray layers. That is, this seems that is also a type of the ceramic that goes to the chip. And then if it is, how much will be the RTH, expected RTH?
It's really hard to say, to be honest, yeah, because it really depends on the overall design. And there we see, in some cases, we need to be, I would say, similar to other constructions, yeah, which is limiting the performance. But we are somewhere in the overall constructions with 10 dies, 0.5 to 0.7, the range.
With this technology?
With this technology.
And the way that you're going to connect the ceramic to this, it's just a free connection. Is the connection to the copper okay?
It's sintering process again, yeah.
No, the chip to the this is sintering. Chip to the copper is the sintering. What about the ceramic to the copper here?
Yes, also sintering. So what you have here is actually a pre-preg layer, and the pre-preg layer and the sintering forms together the interconnection. So that gives you a lot of stability in the system. Yeah? So you don't get only the adhesion from the sintering, you also get the adhesion from the prepregs next to it. Yeah? But we know it's for us, this is not an easy, the RDH is a critical item. Yeah? And I've seen really nice values there, and we believe we can do better, but this strongly depends how far we can go with the designs. But looking forward to it.
Any more questions? Then we thank the speaker again. So our final speaker for the conference is Daniel He from Mitsubishi. He will speak about silicon carbide solutions for railways, efficiency challenges in high reliability applications. Please go ahead.
Yes. So hello, I have today the honor to hold the last presentation. So let's see now. My name is Daniel He. I'm from the Application Engineering and Technical Marketing section from Mitsubishi Electric in Europe. And I will tell you about our SiC solutions for railway applications. Railway applications are especially interesting because railway requirements are high efficiency and high reliability. And this is, of course, especially difficult. And I want to show you what our solution is. So starting, I would just like to show you how our relationship with SiC has been so far. Here you have a short timeline where you can see we already started with SiC and already saw high potential in the early 1990s. Then, of course, we developed some certain elemental technologies and already had first prototypes in 2006 and so on, where we already saw the efficiency and power loss decrease by using SiC technology. And afterwards, we also brought already in 2010 our first commercial product on the market which utilizes SiC technology. And afterwards, more and more products, let's say more and more applications were available where we could use the SiC technology to bring a benefit. And of course, this also goes hand in hand with more products in which we use SiC. We have a different variety of products, ranging from small modules, which are used for, let's say, home appliance or white good applications. We have industrial products for industrial applications, of course, and also high voltage products for high voltage applications such as railway. This slide summarizes the key commercial products which we have released in the early 2010 era. So we started with an air conditioner, when we launched a CNC driver unit. In between, we had the SiC inverter. In 2015, we had a whole traction inverter, which uses full SiC power modules. And this is also installed in the so-called Shinkansen, which is the bullet train in Japan. And also, we launched then also the so-called DIP IPM, which is a small module for white good applications, such as aircon. What I just wanted to show you is we have already many SiC converters in the field. They are operating reliable since 2010. And we see the highest potential when using SiC in applications where the operation time is quite long, because if operation time is long, then the potential to save energy by the high efficiency of SiC becomes more and more dominant. And of course, other applications which require SiC are applications which require high efficiency, or let's say high power density, for example, in motor and transformers. So within all these applications, one of the most demanding applications is, of course, an application which requires high efficiency and high reliability. And this is exactly railway applications. The efficiency, of course, we will get by using the SiC MOSFET technology. And reliability is another topic which is quite difficult, of course, because there are many different aspects. But we have, of course, used technology to make the product as reliable as possible. And this is also proven by our field experience, in which we have no failure since 2010. And in this presentation, I especially want to talk about the bipolar degradation mechanism, which is, of course, still a headache in many let's say manufacturers' heads. And I want to show you how we try to avoid this degradation phenomena. So this is also just for your information. This is a survey which was done in Japan. So unfortunately, this is the reason why it's in Japanese, but it's okay, I think. You can see many different manufacturers, or let's say many different railway operators in Japan, which are in Japanese then, who are already utilizing SiC technology. Although maybe we don't see it here so strongly, but you can see here that we, as Mitsubishi, are already in many different railway applications in Japan. Here you can see, in this column, you can see at which year the system is operating in the field, which technology it uses, full SiC or hybrid SiC, and which manufacturer is behind it. For example, if your Japanese is not so good, the three lines are representing Mitsubishi, for example. But of course, we also have Hitachi here inside and so on. But this, I just wanted to show you, we have already many experience and already saw that our product is reliable in the field. And also, with the more applications we have, the more experience we can gain to make the product as reliable as possible. So like I said, reliability, in this case, I want to concentrate on the bipolar degradation. Bipolar degradation is, of course, not so good because it's an irreversible degradation mechanism in SiC MOSFETs. The problem is that in reverse direction, we have a so-called body diode here in which a bipolar current can flow. And this bipolar current can cause stacking fault expansions from basal plane dislocations, which means if we have this bipolar current flow in reverse direction, there's a risk of bipolar degradation which will cause an increased drift resistance or leakage current or even other risks. And this is especially critical the larger the epi layer is, the bigger the impact will be. And of course, for higher voltage ratings, so it's just high voltage modules like 3.3 or even higher, this becomes more critical. And there are basically, let's say, three possibilities how to handle this bipolar degradation mechanism. The first one is really easy. We use an SiC MOSFET and just do nothing. We ignore everything. This is possible. This is, of course, very cost efficient if we don't do anything. But this is, of course, not reliable because in this case, we have bipolar degradation, which is a certain risk in our application. And this is, of course, not suitable for high reliability applications such as railway applications. And that's also why we don't have a module which just operates based on a SiC MOSFET for high voltage applications. The second possibility is we use this SiC MOSFET here and have an anti-parallel Schottky barrier diode here. And this is actually one possibility which we also use for our modules. For example, our FMF750 DC66A uses this combination here. The SPD here is tuned so that in reverse direction, it will take over the current before the body diode will do. And therefore, we avoid body diode operation and therefore bipolar current flow. And this, of course, results in avoiding the bipolar degradation. This combination also we used in this module, and this is also operating since many years in the field and reliable. And where we could prove that this combination can allow us to avoid the bipolar degradation mechanism. However, there's a certain problem with this method. The SiC body diode, the SiC SPD here, needs to be tuned so that it will take over the reverse current before the body diode does. And the tuning is also related to the overall area which it will need to occupy. So in 3.3 kV rating, for example, if we take the MOSFET cell here as 1, then the SPD needs to be already roughly 1.3 times the size of the MOSFET, which is maybe in 3.3 kV, maybe still okay, more or less. Not optimal, but maybe okay. But if we will go to higher voltage ratings, for example, 6.5 kV, then the SPD will significantly be bigger than the MOSFET itself, which is a little bit not optimal, let's say, because the main product is still the MOSFET and not the Schottky barrier diode. And the Schottky barrier diode will occupy 3 times the space compared to the MOSFET. So with this methodology, in 3.3 kV it's okay, but for higher voltage ratings, maybe in the future, we have a huge loss of available substrate area, and of course the power density of a module will go down. So the next step which we did is we embedded the SPD inside the MOSFET. Here you can see this is the MOSFET area, and here in the middle we have a small area where the SPD is embedded inside. And by this method, we have also brought out a new module, the FMF800 DC66BW, which uses this SPD embedded technology. By this method, we can keep the Schottky barrier diode in order to avoid bipolar degradation and also make it overall more compact. For example, if we go to 3.3 kV rating again, if we embed it, then we will roughly go to 1.1 the size of the overall original MOSFET here. This is also because we avoid the additional chip here, which will also increase the area, the available substrate area, which we can use, of course, for MOSFET chips. However, this is this embedding of SPD, of course, we can do, but why? Or of course, also other manufacturers can do. But why did we not do it before? There's a certain disadvantage when we embed the SPD inside the MOSFET. And this is the surge current capability. By having this embedded structure, the surge current capability is not so high in normal SPD embedded SiC MOSFETs. For example, you can see it here. We have 4 chips, and here you can see that here we have a small area which is for the SPD here as well. And in case we have a surge current event, the current in reverse direction is quite high. So here's a graph, current versus voltage. So in case of a surge current first, the current and the voltage will rise more or less linear because most of the surge current in the start will go through this area here, through the SPD like normal unipolar operation, because the SPD is a unipolar device, of course. Yes, we'll go through here. But as the current increases, the voltage drop here in this area will also increase, and this will activate the body diode here. And then the body diode will also conduct. And the body diode will conduct a bipolar current. This bipolar current consists of majority and minority charges. And this will also affect the overall resistance due to conductivity modulation. So if we go here, then the voltage will go back a little bit. The area where this happens, when the unipolar current through the SPD will change to a bipolar current due to the body diode, we call this voltage here the so-called snapback voltage. And the snapback voltage is very sensitive. It's a very sensitive parameter. A snapback voltage will depend on the overall SPD width here. So, for example, a variation in the snapback voltage of roughly 1 volt is already due to a variation of 0.1 micrometers in the SPD width. And 0.1 micrometers is already not so easy to handle in the automated process way. And if, for example, the SPD width between this cell here and this cell here varies a little bit, then the snapback voltage will also vary a little bit. And for example, here, if it's small, if the width is smaller, then the snapback voltage will also be smaller. And then here it will go, cell A will go into bipolar conduction first. And suddenly, all the surge current will go through this chip here before the other chips become activated. So this is like a current crowding process in one chip because of small SPD variations. So the current will always crowd inside the MOSFET with the smallest SPD, and this one will determine the surge current capability. So the whole surge current capability is just determined by one chip, which is, of course, very small, let's say. And our method to increase the surge current capability is to use so-called BMA cells. Here you can see, again, the SPD embedded here. And here, in a certain area, we intentionally put a P-well here to make a body diode inside. This body diode will not operate in normal operation, but just in surge current operation, so like in emergency operations. If a surge current goes through here, of course, first unipolar current will flow here, but at the same time, this body diode will activate. This body diode will take over a current and let the bipolar current flow through here. This bipolar current will cause conductivity modulation in the neighboring area, which will reduce the drift layer resistance here. And by reducing the drift layer resistance, the current density in the other neighboring JFETs will increase, which will, in this case, activate the neighboring body diodes immediately. And this, of course, will propagate through the cells. So with this methodology, instead of a sudden current increase in just one cell, with this we can almost simultaneously activate all the cells. So the whole surge current capability is, again, more or less, let's say, the sum of all these chips here. And this is how we get similar surge current capability like normal MOSFETs. And this is how we also avoid this disadvantage of SPD-embedded SiC MOSFETs. And this is our solution. Of course, this is regarding reliability and surge current capability, but of course, we also modified the chip a little bit in this newest generation of SPD-embedded MOSFETs by optimizing the switching speed. So we could, for example, here's just a comparison between our SPD-embedded MOSFET and the previous one, which was external SPD and MOSFET. We could already reduce the switching loss by 67%. We, of course, also adjusted the package so that the RTH becomes smaller, in this case 29%. But in general, if you look at the whole system, when I did a small simulation based on datasheet parameters, you can see that we also optimized this product compared to the previous one and had a 62% higher output current at 7 kilohertz, just as an example. So with this new SPD-embedded MOSFET, we have a high reliable product, which is also more efficient than the previous generation. This is like our answer to the railway application requirements. This is just a short lineup. At least at Mitsubishi's side, we just use this package here for high voltage SiC. MOSFET because this package is quite symmetrical and low inductive, which is, of course, a key requirement in utilizing SiC. In this case, we have many different ratings, and now the new technology with the SPD embedded for the SiC MOSFET. What I just want to tell you finally, at least from our viewpoint, we have very robust and high quality products, which also are based on, whose quality is also based on very good field experience, where we don't see failures. And the other main message I want to give you is SiC is best suited for applications which operate a long time during the day, because there we can save the most energy due to the high efficiency of SiC. This is especially true for railway applications. And by embedding the SPD into the MOSFET, we can avoid bipolar degradation. Using the BMA cell, we can also maintain a surge current capability, which is comparable to normal MOSFETs. And we achieve a very high power density because we have more available substrate area inside the module by embedding the SPD. And also the performance itself, based on the simulation, show that we have a very high efficient, low loss performance. And this can lead to better cost optimization and energy saving. Well, thank you very much. I'm not sure if there's time for questions, but otherwise, you can find my contact.
Thank you so much, Daniel. We have time for a question. Victor?
Thanks for your very nice talk. Just to understand better, for the SPD that you have integrated in the chip, you're able to increase the surge current capability by designing in a way that you have the P junctions turn on when there's a high level of current. Is that what it is?
Exactly, because by embedding, usually, the technology is, I think, not super new, because you can always embed the diode inside the MOSFET. But if you just do it like this, the surge current capability just depends on one cell. And like you said, if we just take a small part of a cell, less than 1% is already enough from the whole MOSFET, and put in like an intentional body diode inside, then we can make it so that all cells will contribute to the surge current capability, and this is how we could increase it.
So I think you were talking about a merge pin Schottky diode. So when you have a Schottky diode, right, you have the P barriers for the reverse leakage, but those are not supposed to turn on. It's supposed to be a unipolar device. If you design it in a way that it turns on to help you with your surge current, then those P distances start to become smaller. So you pay a penalty in the on-state conduction, if I understand your
Actually,
method.
The P part itself does not turn on under normal conditions, normal operating conditions.
Yes, it doesn't turn on in the normal operating conditions, but in order to get it to turn on when there is a surge, the spacing of that P plus cannot be the same as the regular SPD. They need to be designed differently. So in the on-state, they leave less space for conduction between the P when you don't have a surge event. Anyway, we can take that offline. One more comment was that you mentioned that the bipolar degradation is not reversible. It actually is. It's been shown in diodes, right, where if you have bipolar current, it gives energy for stacking fold expansion. If you anneal that device now that has degraded because of the stacking folds, it's actually going to go back to its original state. And for MOSFETs, I don't think it has been shown. I've shown that for JFETs. For MOSFETs, because you have the oxide and all kinds of other defects and issues, it was never shown. But it is reversible. Obviously, it's not the mode to operate, right? Basically, have the device degrade and bring it back, and you need about 300 degrees to do so. But certainly for the diodes, they come back to life. When you anneal, and JFETs come back to life. If I get my hands on some MOSFETs, I can play around and see if I can revive them. But anyway, just a comment that it's not like a permanent.
Yes, maybe that sentence was very strict, let's say.
Yeah. But for your application, right, it is permanent because it will
usually in field we don't anneal the MOSFET again.
Yes. Thank you so much.
Okay. Any more questions?
6.5 kilowatt.
Wait for the mic.
For the 6.5 kilovolt, can we use this similar diode because I think this in this case, then you have shown that we need a very big. One of the benefits of this technology is that when we go from 3.3 to 6.5, this body diode could be smaller because it goes embedded.
Yes.
But you haven't shown here that when only later when you have embedded, you have shown only 3.3 application and benefits of that one. If we go to the 6.5, I think we will be a little more challenging with this body diode that is embedded. Have you tested that one? Have you implemented that one to see what will happen?
The 6.5 kV product itself still under R&D stage. But of course, the embedding of a MOSFET is definitely a way, because otherwise we cannot avoid bipolar degradation, which becomes, of course, more critical in 6.5 kV. And embedding it is the only, let's say, reasonable way to maintain a reasonable product regarding the size which is used.
And this is also, I think, do you think that this solution can be applicable for the 6.5 kilovolt as well?
Yes.
Do you have such a power module? For 6.5 kilovolt?
6.5 kilovolt? This I'm actually not sure, because it's an R&D stage. This, I think even my colleague from R&D knows better.
Okay, so that we already finished the development of 6.5 kV Schottky barrier integrated one. Already we have we published the papers 3 or 4 years ago, but we are now developing with BMS cells, avoiding that short surge current. Then, so the next year or the next year, we can provide some samples. But it's up to the market. 6.5 cases, very limited application required. Now, so that everyone wants to use 3.3 kV parallel connection as the serial connections. Then, if you are interested in and you have a big market, we can provide.
Okay. The reasoning that you have said that if you go to 6.5 kilovolt, then we need such a big diode, then we have embedded. Actually, we don't have 6.5 kilovolt.
Yeah.
Maybe it is not good like a motivation to go to this diode using. But I agree that we need such a diode for this bipolar degradations, or that is said. But maybe this reasoning could be not so much applicable.
Okay. We have one more question from Victor.
Basal plane dislocations are basically something that you can test for when you make the device. So it's not a reliability problem, it's a yield problem. Once you finish fabrication, you can actually bias the device in a way where you can turn on the internal PN junction. So get that bipolar current. If there's a concentration of basal plane dislocations, you will start to see degradation. Obviously, you have to do a little accelerated testing, because when you're in the in the fab and in the business of selling devices, you cannot have long testing. But it's something that if you do it right, can turn into a yield problem as opposed to a reliability problem in the field. Of course, if your yields are going to be very poor because you have a lot of BPDs, and as the speaker mentioned, the higher the voltage, the worse the problem, because the stacking faults have more room to propagate in a long drift layer. So that's very catastrophic. But certainly you want to turn this into a yield issue, an reliability issue for the sake of silicon carbide, right? We don't want to be thought as people that make unreliable stuff. So anyway, just a comment.
Okay. Thank you. I think we end the session there. Thank you, Daniel, again, the speaker. And I give the word for closing remarks to Hansi.
That one's better, yeah. Thank you very much. It feels almost a little bit sad to say that now we're going to have closing remarks. I think it feels like it was ages ago we had SCAPE, and now finally we have it again. And a lot of things have happened since last time. And I'm happy to see that we are almost 100 registered participants here, and we have more than 30 speakers at the conference. So I think it's great, and we have many of the best specialists in the world here today. We started with looking at the strategic initiatives around the world, and we could happily confirm that there is still a very big force on moving wide bandgap technology forwards, both in America, in China, in Europe, and so on. So it happens everywhere now, and everyone is convinced that we're on the right way and that we need to invest more in this technology. We also had then the device manufacturers telling what they are doing, and sure, they are doing a lot, many things. I have a long list of things here I could talk about, but it's already late today, so let us not do too much about that. An interesting thing about the outlook from Yole was to get a message that what we have waiting for a long time, the wafer costs for silicon carbide, that they will probably soon come down. So you showed us pictures of how the capacity of production for substrates is increasing, and it seems now for the first time here that it's increasing faster than the need for substrates. So of course that's very welcome news, because the substrates cost is a big part of the total cost. Then we have had also quite many presentations about applications. And of course, the applications are important because those are the ones which are driving the whole field. And we see some new applications now. Of course, automotive is very big, and it almost takes it all when it comes to silicon carbide. But we see it also starts with gallium nitride. But now we see also some other applications which are interesting, in my opinion, like aviation and marine and fuel cells and so on. So the scope is widening, and that's what we have been waiting for. We even see now from the predictions from Yole that we will see some more industrial applications coming. I think now also in the end, we saw things happening which at least I have been waiting for long, to see some really new innovative concepts for module building, or let us say advanced packaging. So what we saw here now in the afternoon with the PCB-based or substrate-based technologies for packaging, I think seem to be very promising for the future. We can get low inductance, we can get good thermal performance, and it seems there are also possibilities to get good reliability. But everything hasn't been investigated yet, and maybe that's good, because then we still have some work to do for the future. And finally, I would just like to say, we are very happy that you came, both those who came here as audience, and of course to all speakers. And some of you have been traveling from far away, from the United States and Japan and Korea, and a special thanks to you. And especially from the Wide-Bandgap Power Center, we would say, thank you for coming, see you soon again.